Welcome to Zero Knowledge, a podcast where we explore the latest in blockchain technology and the decentralized web. The show is hosted by me, Anna.
And me, Frederick. In this episode, Anna and I sit down to talk about the fundamentals of a blockchain. What's a block, what's block headers, state, history. We hope you learn something new. So today we're kicking off with another Blockchain 101 episode. We're planning to make this into a little bit of a series, trying to explain things sort of from the ground up, first principles kind of way, and then let people draw their own conclusions from this knowledge. And we're digging into the actual blockchain today. So what are blocks? What are headers, block bodies, blockchain history and state? All these terms kind of get thrown around a lot, and it's not necessarily entirely clear what it actually is. So let's see if we can explain it today.
So the inspiration for this is also, we've actually had questions from some of our listeners. There's some episodes where we definitely just kind of like assumed the knowledge and just sort of said, yeah, block header, etc., storage. And here with this episode, we actually decided, why don't we just like dig into this, create that intro so that people can reference back to it if they get a little bit confused as to what we're talking about. So maybe to kick off, we could start by explaining what a block is.
So I think there's a lot of different ways to approach this explanation. And through my experience of trying to explain this to people, it's a varying degree of success depending on what you choose. I choose to not go into too much detail because it usually just distracts from the overall concept. So I like to break a block down into two pieces, the block header and the block body, because this is functionally what we deal with in a blockchain client code. And they're sort of the two pieces of data that usually get sent around over the network. So a block header is essentially like a fingerprint of a block in the blockchain. So it has a hash, it has a parent hash, so essentially a hash that is linking to the previous header or to the previous block. And it has a bunch of metadata around what this block contains and what it does. So it might have Merkle roots sort of as fingerprints of what is in the block. It has authors, it has a block number, things like this that just kind of metadata and fingerprints of the block itself.
In thinking about this, I kind of get this idea of when you had libraries and you had those index cards and you had sort of just the basic information that you needed to be able to find the book and get the full information. So it's a little bit like the index card that can be easily, you can have a lot of them, you can look through them really quickly and not have to dig into each book or block.
Yeah, I think that's a good description. Yeah. If you're just curious of like what the blockchain, like how long it is, what's the latest number, or like what's the Merkle root of this block, then you don't really need the block body. And you only need this index card of the block.
Another question that just kept coming up, and this is a word that we're going to be using. I think you've already used it twice. So I had my mother asked me after listening to one of these episodes, "What's a hash?" And I think we definitely assume that everyone knows what a hash is. I believe back when we did an episode on proof of work versus proof of stake, we did actually go through a little bit of a definition. But I think it's worth it today to kind of redefine what a hash is, because we are going to be talking about them a lot.
Yeah. So, I mean, like you said earlier, we assume a lot of knowledge in a lot of our episodes, but the point of this series is to try to not assume so much knowledge. So I think that's a fair point to try to dig into. And hashes, I feel like they're relatively hard to explain because they're actually there's not that much analogy to be made in like the natural world. You take a bunch of data and run it through an algorithm to spit out a finite number of bytes. So in a 256-bit hash, you have 256-bit representation of what the input data was. And of course, with 256 bits available, that's a hell of a lot of different sets of data that you can represent uniquely with this hash. But I think the hard thing to get intuitively is how do you get from like a big chunk of data to limited 256-bit size data.
And maybe one other feature, though, like to me, it's partly this like large piece of data turned into a smaller piece of data that references back to that big piece of data. And the other is that is unique.
Yeah.
Or that it is not something where running other pieces of data through that same algorithm will result in the same hash.
Right. So the way I usually just say it if I'm trying to explain a hash to someone that isn't interested in knowing what it is I say it's a fingerprint. So it's a fingerprint of the data. And a fingerprint is unique to the extent that, probabilistically unique. And with hashes, you have the same problem. You have this thing called a hash collision that can happen. And sometimes researchers even find ways of exploiting, like finding deliberately these hash collisions. So that's happened for like some older hashing algorithms like MD5. And this is actually a really big security vulnerability in cryptographic hash functions, is finding hash collisions. And with the better ones today, like SHA-3, there are no known collisions, and the better we get at writing these functions, the less likely it is that there will be a collision.
And by collision, you mean two hashes
that are
two pieces of different data resulting in the same hash.
Exactly.
Cool. In our podcast on proof of work versus proof of stake, we talked a little bit about how to create a hash. You basically take a piece of data, run it through an algorithm, and this results in a new piece of data. But I think the question here is there a way to go backwards to get back to that original piece of data from just looking at the hash?
No. So now we're talking encryption. And I think that's the key distinction here that is usually overlooked, and it can be confusing. So a cryptographic hash function is a one-way function. There is no way to extract the original data out of it. So, I mean, if you just think about it, it's obvious because you could go from a gigabyte of data to 256 bits. There's no possible way that you could reconstruct a gigabyte of data from 256 bits. So it's a one-way function. And the way you then use the hash, say, I want to prove that this piece of data is the same as the one that was hashed to produce this hash. Then you need to rehash your original data and compare the results. You can't go from one end to the other and then like compare the resulting data.
So then I think your metaphor of a fingerprint is perfect, because by looking at a fingerprint, it is unique maybe to that individual, but it doesn't, from that fingerprint, you cannot reconstruct the individual. However, if you have that same individual, like maybe the same exact DNA, exact everything, they will have the same fingerprint. I mean, that's like kind of maybe a bit of a stretch, but yeah.
Yeah. So the two pieces that I mentioned as the block is the block header and the block body. Now, the block body actually contains all the transactions that we're interested in. So a blockchain, it consists of blocks of transactions. And really, like, the block body could contain any data, and it would still be a blockchain. But the useful way to think of it is transactions into this chain. So for Bitcoin, it would be a normal like UTXO type transaction, and in Ethereum, it could be anything from deploying a contract to interacting with one, or just simple value transfers.
Maybe we can talk a little bit more about the transactions. You just mentioned that in Bitcoin, transactions tend to be a transaction of value, which I think we all conceptually can understand. But in Ethereum, you can do transactions that maybe have no value. You see that sometimes. You see like a transaction with like 0 ether. And there you say it could be a deployment of a smart contract. It could also be, as far as I understand, sort of storage of data or something like that. And I'm wondering a little bit what that looks like.
Right. So I think it's useful to think of a transaction as just any arbitrary amount, like any arbitrary data that you want to include in a blockchain. This data can obviously be interpreted in different ways. So this is what we build into a client is, we might have a transaction type. Ethereum transactions set a gas price, a set of maximum gas to be used. It has the value. Like you said, you can have a 0 value transaction, but that would still cost gas. So it would still cost you some amount of ether to, get this transaction included in a block, but it might have no actual value transfer. So what you're paying for then is simply the data. And the data in a transaction is just that. It's a string of bytes. There's not necessarily any interpretation put on it. So if I want to publish a picture to the blockchain, I can just include that in my data for the transaction. But I might also include like a function signature and the parameters of a function call to a contract. And then that will get interpreted by the client as saying, hey, this transaction wants to do this with that contract.
You sort of mentioned you could put a small file or something like that. Is there a limit to this? Like, are you able to put a song like in a transaction and then it lives on the blockchain forever?
Yes, you are absolutely able to do that. And a lot of people have. So there is a max code size on Ethereum, and I believe it's 24 kilobytes. This is a configurable value. So if you're running your own chain, you might have a different max code size. But essentially it means that you can put any 24 kilobyte blob of data on the blockchain. It might cost a lot of money depending on when and how you do this, but it's absolutely possible to put a picture or a song or whatever you want on the blockchain.
I feel like I also heard, just as a small anecdote, I feel like I was watching like a Zcash interview with Zuko, and he mentioned something similar where like there'd been like a love letter written and put into the blockchain. And I guess that would be that. It would be basically just be a small essay, a small letter. Yeah,
there's a lot of examples of that. There's a lot of fun, creative, cool uses of doing that. We've actually at Parity have received job applications through the data field of a transaction.
Wow, that is so cool. Definitely creative. I hope they got an interview. Sweet. So we've kind of covered a few things. So we've covered what a hash is, what a header is, what the body's made up of, and kind of some of the nuances of transactions. One other word that comes up a lot is the nonce. And the nonce, as I understand it, really becomes relevant when you talk about mining. But I think it's worth explaining here for us to like understand really what a block is.
Right. So in a proof of work blockchain, to prove that you have done work, there's some hashing algorithm. So we're back to the hashes. And you take one constant, which is the block, and then you have the nonce. And actually, we checked on Wikipedia earlier to find out what nonce means. I only know it in the context of programming and this kind of stuff. But it's actually like a one-time placeholder word type thing. So when you're studying infants and you like try to see if they've learned plurals, you might say like, here's one wag, these are two, and you ask them to complete it. And if they say wags, then that they've learned plurals and not like memorized the specific word. Anyway, as an aside, the nonce is just a number. So it's just an integer. And you take this fixed constant block and you take the integer and then you hash both of these together and out pops a hash. And then according to your proof of work algorithm, there's a difficulty requirement of this output hash. And usually that's just the resulting hash needs a set number of prefixed like zeros. So it can really be any arbitrary, like you have 6 ones at the start of your hash, but usually it's just a number of zeros that determines your difficulty. So if you take the block and the nonce, you hash them both and you get a hash out. If it has 6 zeros, then you're good and you can submit this block to be like it is now mined and you can submit it to the network.
And you'd be actually given the reward if you achieve that.
But if you don't get 6 zeros in your output hash, the only thing that you can do, because your block is fixed, is increase the nonce. So you just iterate through, you try 1, you try 2, you try 3, and then eventually you'll find a number such that this piece of data is hashed to something that results in 6 zeros at the start.
So it is really just like it's a number that's like the number that's going to change. It's going to, maybe you just go up by 1 each time you do the hash. And I think that's sort of when you mentioned that it's like probabilistic, it's the idea is that you'll actually do this. Like the idea that you try the header and 1 nonce, and on that first try you get it, is very unlikely. What's more likely is that you're going to be doing that hashing process hundreds, maybe thousands. I actually don't know how many times, millions of times. So you're doing it millions of times. And out of that million, 1 nonce, 1 version of the nonce will actually result in what you're looking for, which is that six zeros at the beginning. This is like all theoretical, but like you want some qualifier to that resulting hash. And one of the nonces, or one of the versions of the nonce, will actually result in that hash. But it won't, it's very unlikely that it's just like first time and then you win. It's a bit like, and I think this has been a bit compared to lottery, where you're just supposed to like play and play and play and play and play and play, and there's a probability that you're going to win at some point. Yeah.
So it's definitely a probabilistic game, except that the difficulty is adjusted such that, on average, you will always find the solution within the block time. So for Ethereum, that's 15 seconds or something. And all numbers are equally probable of being the number that you want to get the right nonce, the right hash. And so like what mining pools do, for instance, that are like a conglomerate of individual miners, they will, start miner number 1 on the number 1, and then miner number 2 starts at number 100,000 or something. Then miner number 3 starts at 300,000, and then they just go individually from there. And so together they're like parallelizing the search, and therefore it goes faster. You would do the same thing like if you have multiple GPUs mining, for instance. You start each GPU at different places in this search space.
So now I think we've covered like an individual block. We know what a block is. We sort of know how they deal with each other. We kind of mentioned that you're hashing the previous block's header or previous block, and that's being brought into the new block so that there's a record of like what came before, and there will be a record of what came after.
So there's only a reference in one direction. If you have all the data, then you could construct a reference in both directions.
Okay. In this blockchain, this is where you could have things like history or those little pieces of data and all of that stuff. That all can exist in the blockchain. But you hear like people talking about state database or this other piece of the puzzle to actually access this stuff. So let's start talking a little bit about what a state database is.
Yeah, so I think just talking about the blockchain in itself is useful to understand what the chain is, what gives it its properties of immutability and all that good stuff. But the blockchain itself is usually called blockchain history because it has all of the data and it has all of the transactions that have ever happened on the chain. And this can change. If you changed any of this, then the hash would turn out different, and you can prove that, this block is invalid because it's changed, and it would break the whole chain. But to make this chain useful, you actually need to do some optimizations. Because let's say you want to know what the state of a contract is in. Now you need to play through all of the transactions in all of the blocks to find where it was deployed, and then find all the transactions that modified this contract in some way. And then eventually you'll have what the state of this contract is in. So you can construct that from the blockchain alone. But it's incredibly slow, obviously, to iterate through all the blocks in the chain and replay all the transactions all the time. So what you do is when a blockchain node is syncing, is that it's downloading the blocks, and it starts with an empty state database. And then as it's downloading the blocks, it's playing all the transactions and storing all of this state in the state database. Then it goes on to the next block, plays all those transactions on that same state database. And then at the end, you have a current state of, what the state of all the contracts are in and everything. But you have no history in there.
So it's just it's like a snapshot of that very moment. It's not going to say, as I understand it, you can go backwards and look at the state at different times, but the state database, as we're discussing it, will only show the latest.
Right.
Meaning, if a change has been implemented somewhere, you won't know that there's been a change, and you won't know what existed before. You will only see the latest state of the blockchain.
That's right.
So when you talk about that snapshot, maybe let's go back to some of the block fundamentals that we just talked about. So can you help me understand where exactly the snapshot is happening? What is it, a snapshot of the latest transaction? Is it a snapshot of only the latest block header? Which parts of what we just discussed is being captured by the snapshot and which parts are not?
Right. So I think it is a snapshot of the entire state of the entire blockchain. And it is a point in time thing. And the time is between each block. So you'll never have a state database that is, the state of, this particular transaction or anything like that. It's after or before this particular block. It doesn't dig into transaction level things really. So you play all of the transactions of a block and then produce this state database point in time view. And I think a useful way to think about it and describe it is, if you think of a blockchain, it has one smart contract on it. The only thing this smart contract does is store a number. And let's say it's deployed with storing the number 0. After this block where we deploy this contract and we store a 0 in this contract, the state database has a key to this contract and it has a value that is 0. Mm-hmm. Now we send a transaction that updates this number through the smart contracts. We send this transaction, it contains the function signature, and it contains a 1, which is the number that we want to change it to. Now, after this transaction has been mined, included in a block, the state database after this block gets updated to the same key holding the value 1 instead of 0. Now, we send another transaction changing it back to 0. And, same thing, we create a transaction, it gets mined, included in a block. The state database after this block will now contain a 0 again. And if we just look at the state database, we have no way at all of knowing what the value of this contract has been in the past. We just know that it's 0 right now. We don't know if it's changed, if it was once this or that. We only know that right now, after this block, it's 0.
So that change from 0 to 1 and 1 to 0 is completely lost in the state database.
Right, which is why we call the blockchain itself history, because all the transactions are obviously all still there. They're all still in the blockchain. So if we actually want to go back and look at, what was this state of this contract at this point in time, we can either go back and replay all the transactions again up to that block that we're asking for, which is slow, or we can run what's called an archive node, which saves all of the states between all of the blocks. So that way we can easily say, okay, give me what the state was for block 1 or for block 10, because we're saving all of them.
And that query would be a lot faster.
Right.
So the state database, is the purpose of it just speed of accessing data? Is it really just like use this database so that you're not kind of going through the entire blockchain every time you want to actually see what's going on?
Yeah, pretty much. I mean, it would be prohibitively expensive without it. Like, you basically wouldn't be able to run a network without a state data. Like, because creating a transaction would be, both creating and validating a transaction would be so incredibly slow that you would not be able to process almost anything.
Was the state database created and deployed at the same time as like a Genesis block? Does that always come in tandem, or is that something that's built afterwards?
No, it was thought of in advance. Like, it wouldn't, because it would not really be possible to have an Ethereum-like blockchain without a state database. It was something that was designed for from scratch.
So now let's think about some ways that nodes or clients kind of are interacting with this. We talked about this in our previous Blockchain 101 episode, how the full node has the full blockchain. That means the full nodes, and kind of in reference to what we've just spoken about, the full nodes will actually have the body and the header, and they will have all of them in a row.
Yeah.
There's a difference there with a light client. We talked about it last time, but we hadn't really explained the headers and that distinction.
Yeah. So I think there's 3 useful types of clients to talk about. The one I just mentioned, which is the archive node, there's a pruned node, and there's light clients. And we've talked in the previous episode a little bit about light clients, and they only have the header chain. So it's only this chain of headers. They don't have block bodies. The pruned node has the full blockchain history. So it has all of the blocks, like you said, and it has a couple of the latest states. The reason you'd want more than one states database just for the latest block is to be able to roll back in case of a reorg or technical reasons. So it's a full or pruned node will save a couple of state databases as well. And an archive node you would really only run for research purposes, because then you're storing every single state ever. And obviously this takes a lot of space.
This is just to sort of have a backup of everything, I guess.
Yeah, I mean, all of the data exists there anyway, so there's really no benefit to the network that you're serving or anything like that. The only reason that you'd keep it if you're looking at these old states a lot, and it's too expensive to keep reconstructing them all the time.
So a few weeks ago, we interviewed Phil Diane about storage rent. And there, I know that the question about state and history came up a lot, about pruning. So say you were trying to get rid of, I don't think we defined pruning exactly, but maybe we can talk about it in the context of this storage rent and the fact that there's actually data sitting on the blockchain, using up space, making those blockchains just bigger and bigger. And so every node is going to have a bigger and bigger chain to download. Right.
So in this discussion, there's 2 useful things to think about. It's the blockchain history and it's the blockchain state. And so like we said, the blockchain history is immutable. We can't really change anything without destroying the chain. And that's kind of a reality we have to accept there. There's things we could do there as well, like snapshotting and recomputing things, whatever. But the state database is something that we can do quite a lot with because it's kind of outside of the blockchain. The only thing we have to reference this state is the Merkle root in the header. So we can sort of modify this state to whatever we want and then include that Merkle root in the header, and things are still fine. So one thing that we could do is actually remove things from the state database. So right now, all the contracts ever deployed are in the state database. All of their data that is in these contracts are all in the state database. I think this data is a couple of months old, but I got this from Peter from the Geth team. He has a breakdown of all the contracts and how much storage they have. The top storage heavy contract is CryptoKitties, and it's storing something like 250 megabytes on the blockchain. So if if everyone stopped using CryptoKitties today, and then in 10 years, it's still there, but no one is using it, it's 250 megabytes of garbage data because no one uses it, no one values it anymore. Should we just let that sit there forever, or should we remove it or force someone to pay to keep it around? And that's what the whole storage rent discussion is about. And we can actually remove it and things are fine, because you can always go back into blockchain history and resurrect all that data. It's just a lot of work to do so.
And it's funny, the number you just mentioned, 250 megabytes, is not a big number when you just think about data storage. But I guess to give some context, is that's 250 megabytes that would have to live on every single full node.
Forever. And this is just one contract. And the goal is to have millions of contracts that are as popular or more popular than CryptoKitties. So how do we deal with millions of contracts wanting to store 250 megabytes each? Yeah.
I think that's great, because it gives a little bit more context to the problem that we were trying to discuss in that previous episode. One thing that we've mentioned a couple times throughout this episode is the Merkle Tree, or the Merkle root. We didn't want to necessarily define it right at the beginning of this episode, because it sort of is a topic in and of itself. But I think it would be worth our while to sort of come back to it now and try to give you, our listeners, a little bit of a sense of what that actually is. So why don't we talk a little bit about the Merkle Tree? What's a Merkle Tree?
So a Merkle Tree is a data structure, a very general data structure. It is a tree in the computer science term of a tree. Without knowing what that already is, I guess it's pretty hard to explain. But if you imagine a tree where there's a tree trunk, that's usually called the root, and then it branches out from there into different branches, and at the sort of bottom or top layer, depending on how you orient your tree, there's pieces of data, and these are called the leaves. So let's say we organize 10 numbers into a Merkle tree. We'd have the numbers 1 through 10 at the leaves. And then we'd hash number 1 and 2 and make that a branch above that. And so the hash of those are stored there. And we do this for all of them. So then we go up one level, we have much fewer nodes, and in these nodes we just store the hashes of the children. And then we go up that way until we're at the top, where we have one root hash that represents the hash of all the other data. So if we change any one leaf in this system, the root hash will change. But if we change number 10, then it's just that particular branch of the tree that has hashes changing. So to prove that we've only changed the number 10, we can actually skip a lot of the data and only provide data for that branch of the tree, and then the hash of the rest of the tree. So then we can kind of skip having to reshare the entire tree, and can just reshare sort of the path that we've changed.
The reason you would use a hash tree, like a Merkle tree, is that it would provide a means of proving the integrity and validity of the data contained, and yet it would require very little memory or disk space or information, because all you're really getting is that last root hash, and that's still proving that all of the other data is valid. But I gotta say, this is only the tip of the iceberg when it comes to Merkle trees. This is actually like a huge topic.
It's a really interesting topic, and you can dig into more of like how Merkle proofs work, and this is how you can sort of confirm that a given state is correct and that kind of stuff. And it's a very fundamental piece of any blockchain, really, and it's definitely something that's worth learning about. But it's definitely a deeper topic. Like it's actually quite hard to explain, especially without drawing things, and even being able to draw things, it's pretty hard to grasp the implications of these various properties of this tree.
I think that we've covered a lot of ground with this episode. We've looked at these blocks. We've looked at the way that they work together. We've hopefully shed some light on what people mean when they say like clients and pruning and history and state and what actually can exist in a transaction. I hope that our listeners liked it. Frederick, do you have any last thoughts?
If you liked it or didn't like it, please give us feedback. We're on Twitter, email hello@zeroKnowledge.fm or Twitter @zeroKnowledgeFM. And especially with this series, I'm really keen on hearing any feedback, and what do you think we should dig into next, and what did we explain well or not so well. And thank you very much for listening.
Thanks for listening.